My name's Nick Favazzo. I am part of the Motorsport team. I've been at uni for longer than I care to admit. But benefit of being there that long, I've been on the team for a long time and I've learned quite a bit about vehicle dynamics. As a result, Carol's asked me today to take some of his lecture on Ackerman steering and the linkages associated with steering. That part of the course is accessible. I'm not 100% sure if my next lecture is, although it's probably best not to gamble with that. So first up, I'll be going over some of Carol's own content, and then I'll be breaking into motorsport stuff and steering in a little bit more detail. So the image that you can see on the screen at the moment is the easiest way to sort of visualize what Ackerman actually is. So if you take the perpendicular line of the wheel direction of the front two wheels and the rear axle plane, you can see that at the point of intersection, that is your centre of curvature. So if you had the centre of mass drawn in here as well, you'd find that the whole car rotates about that point. The Ackerman condition was originally developed and theorised around horse-drawn carts to not dig into gravel roads. Back when they had quite thin wheels, they'd cut into the gravel pretty easily, so it was pretty high importance back then. Nowadays, the benefits of it are elimination of wheel slipping or tyre scrubbing, and it also reduces steering effort because you're not trying to push the tyre across the ground. Benefits of having non-Ackerman I'll go into a bit later, but the design of such is always pretty important as well. But at the moment we're just focusing on pure Ackerman suspension. So the next image you can see here is of what you traditionally see in an automotive or car. So you can see O and F and OE to E is your idler arm and your input, whereas DC is the obviously connecting link between those. In a lot of cars, that's actually replicated by a rack and pinion gearbox. So the rotary input is somewhere on here, and there's a set of gears which slide F to E across and put your steering inputs in. This is an 8-bar linkage, and all but two of the joints are revolute. Joints A and B are spherical, and that's mostly to allow suspension travel and whatnot. So just quickly, we'll go over some degrees of freedom analysis of that. So assuming the planar condition, which is the one up top, we have 1 degree of freedom. We've got eight joints by the 1 degree of freedom, and you've got 2 sphericals, so 2 F1s. So 2 by 10, 21 take. Have you guys done mobility systems? Yeah, so this is all pretty straightforward stuff. Spatial conditions, so this is now real life. You've got a whole car in 3 dimensions, so you have to take that one into account. You can see the equation changes for that one accordingly. You can see that it is over-constrained, but that's special geometry associated with 4-bar linkages. Modern cars, as I said before, tend to use a linear input from the rack and pinion gearbox to allow rotational input from your steering wheel. It eliminates links, so you're removing obviously packaging constraints, a bit of compliance in the system. Weight. I've got some examples of alternate solutions as well coming up in my slides, so I won't go too much into that right now. The main thing that you take away from this anyway is in the book, Mechanisms and what we got, Kinematics, Dynamics and Design of Machinery by Waldron. It's your course book. There's an example on page 351, which I'll focus in on this one. So you can see here we've got our Ackerman lines to indicate what's going on here, and you've got all your variables listed. So there is a blow up on that, I believe, on the lecture slides that Carol's uploaded anyway, but that's it's obviously on a different page, so I can't work through that one by itself. Sweet. So that system that I just showed, figure 7.25 of the book, it's on page 350 for anyone with a copy or willing to go to the library to chase it up. There's a really good worked example. For anyone that joins a team, I usually recommend that they follow this with this as our motorsport book anyway, so I get them to follow it through and understand what's going on there. So Essentially, the linkage can be analysed by two slider crank mechanisms acting in parallel with the common input, which in this case is the delta U. All right, we'll zoom back in this one. All right, so you can see there are two U values there. Obviously, one's positive, one's negative. They're both displacement. That being the same because the actual slider mechanism itself is actually what's putting the input in, be it from the rotation, the steering wheel, whatever else it may be. So you get your two equations. So you've got A cos theta plus B cos U, mu equals your R plus U, where mu is your tie rod angle. Again, all these variables are shown in the diagram, so follow that one through. Simple mathematics, maybe not simple, but you're working through the maths anyway and eliminating a lot of the variables, and then you can work it down to get your standard solution, and then you can look up your PQRs from the table in 5.1. I'm not too sure if he's supplied that as a separate course material where it's on LMS, otherwise it's definitely in the book and it's worth reading through and understanding anyway. So following through from that, work through the maths. I'm not going to take you through what is first year maths really. And from that you can then obtain this table here, and based on that this plot occurs. Now this plot is difficult to understand if you're a little bit far removed from what's going on. So x is essentially the distance from the center of the rear axle to the distance of the intersection of the perpendicular lines from the front. So going back to this drawing here, x is the displacement from the center of the rear axle to that point of intersection. Next up, y is the error from perfect Ackermann. So that dotted line going across there, you can see that it's slightly not at zero the whole way across. So it's small mu, it's actually quite a good approximation for the Ackermann condition, and as displacement increases, it tends to not closely follow Ackermann. But for all intents and purposes, you can design around a maximum range of 0 to 1 inches and have the associated ratios on the steering side of things inside your wheel so that you're not actually going outside that close approximation. So yeah, if you've got questions you would like to see that in the book, come up to me after the lecture anyway, and I'll talk you through that again. But the example in the book's really, really good. Me talking through it is just going to bore you guys to death. So follow that one through. The content for this is going to go up. The work solution for this is going to go up anyway if you don't follow the book. But I really recommend reading through this book. It's so much gold. All right, moving on to the actual steering motorsport side of things now. Sweet. All right. So these slides will be going over mostly on steering. Obviously, next lecture will be going on a bit of your suspension and springs, so your 4-bar linkage suspension types and a few others, and how we go about controlling those. So essentially, steering will be looking at how it controls the car, slip angles, how it generates the lats, a bit about slip ratio, and how it actually builds up longitudinal forces as well. So the main things to consider about steering geometry is just tyre slip angles and slip ratios. Now, in the picture that it was up when you first walked into the room, that diagram of Ackermann had 0 accounting for slip angle. Obviously, slip angle changes the direction of the force, and as such, it changes the actual direction of that perpendicular line again. There's another picture in this upcoming slides where we'll talk about that one. Caster and kingpin inclination. The reasons for having those, their effects on the car and the driver's inputs, as well as tyre contact patch deformation. So a lot of what you learn is to make assumptions about things, and one of the assumptions that is generally really bad is that a tyre is infinitely stiff and doesn't deform. So looking at tyre contact patch deformation and how this affects all your calculations and the forces, yaw moments, things like that. So Ackermann, I'll be going into that in a bit more of a real-life explanation, in that it's dynamic toe-out, which is steering of the wheels with movement, and its influence of weight transfer and slip angles, and then I'll have a few slides on the different types of steering systems and solutions. So just first off, I'll be going over some suspension terms. So main axes are longitudinal forces, so straight down the car, the direction you're facing. So when you're braking in your own car and you're rolling forward, that's that longitudinal force that you're feeling. Lateral forces perpendicular to the car centre line generally, and parallel to the ground. Obviously, when you're going around a corner and your cup of coffee spills, that's because of your lateral force. Vertical forces not as big of a concern in analysis and stuff, generally because it's a result of the road you're travelling on, not because of the forces generated by the tyre. Now, suspension travel, this is probably less relevant to this lecture, but for next lecture at least anyway. You've got bump, which is essentially the wheel moving up relative to the chassis. Think of it as going over a speed bump and it's going up, bump. And rebound is just a return direction, so it's just coming back down again. If you see rally cars and they're getting air over a crest of a hill and the wheel going down, that's rebound. You can see that pretty clearly as well, and it looks kind of cool. All right, so the function of steering. Steering's main involvement on a car is to initiate and control yaw. Yaw is a rotation about your vertical axes. So a good way to picture this, if you had 0 yaw and you went around a 180 degree turn, if the car didn't turn around that centre axis, it would actually come around the corner the wrong way around. You'd be reversing out the corner. So your angle is essentially a difference between the front and rear slip angle, and it allows the car to actually rotate about the centre of mass. Another big player in steering is to control diagonal jacking, and this is through caster and KPI, and I'll touch on those in a bit as well. So it's possible for a car to negotiate a corner without any steering angle, simply due to imbalances in slip angles, and this is also possible from different bump heights, different wheel heights, and the associated change in steering angle of each wheel, and the forces associated with that. So if you've got one wheel pointing slightly inboard, and it's more inboard or more straight than the other one, you'll find that that's got a dominant effect on the car's behaviour. So how does a tyre generate lateral force? So slip angles. If a tyre has 0 slip angle, it's got 0 lateral force. If you've got 0 slip angle, you're not turning around a corner at all. So a slip angle is essentially the tyre travelling in a different direction to the wheel, what direction it's pointing, and the diagram is a pretty good indication of what's going on there. So if you're the ground, you're looking up at the tyre, and the tyre is actually turning to what would be the left, you can see that the actual contact patch is being left behind. So a good way to get an idea of this, if you've got an eraser, quite a tall eraser, and you put it on a desk and push down on it, if you twist that tyre, twist that rubber eraser, you'll notice that the bottom of it is actually deformed from the main top plane. So that's exactly what's happening with the slip angle. It's twisting of the tyre carcass. And the energy used to locally deform that contact patch is what creates the lateral force. And the difference in the tyre rotating planes, if you take the rim, which is a steel part, generally you don't assume that that's going to have a bending slip angle through it. So you take the direction that the tyre is actually moving and the direction that the wheel plane is rotating in, and that'll give you your slip angle. So another good way to think of it is a footprint model. So if you've got your tyre slipping out with each one of these, as it rotates around, it's not actually scrubbing across the road, it's actually stepping out smoothly. The image on your right from Milliken again is a physical test they did. I can't remember when it was. This was 1800 sort of thing. It's a thin disc of rubber clamped behind 2 steel discs, and that's where they came up with the footprint model, because they found that when they twist it, it's not scrubbing, it's not scratching the surface, it's actually leaving footprints across the direction. And the difference between that wheel plane again and the path of those footprints is your slip angle. So every tyre is created differently. Every tyre for your road car, for your racing car, for motorbikes, whatever it may be, they all have different designs, different characteristics, different rubber, different construction and different stiffnesses in all the different modes. So generally an increased normal load requires a higher slip angle for a peak lateral force. There are some tyres which go the opposite way from that, and the curves that result from that can be quite peaky and hard to control. What makes a good tyre is the plot that you can see here. So along the bottom we've got slip angle, and you can think of that as your steering angle, and on the left hand side, the vertical axis, you've got your coefficient of friction. and you can think of that as generally a tyre's lateral performance. So if you have the really peaky tyre, the one that's got the most, highest coefficient of friction, about 1.6 or something like that, you'll find that at whatever it may be, 6, 8 degrees of slip angle, it's not too bad. It's really good compared to the other 3 tyres that are on there. But if you've got a driver on there who can't actually control, his limit of control is maybe plus or minus 2 degrees of slip angle, you'll find that the change in force from the tyre is quite drastic over that range. Whereas if you had something like the black line, which is third from the top, which is maybe sitting at 1.3 coefficient of friction, you can see that there's quite a broad range that tyre operates predictably over. And it's this slip angle behaviour that determines a good performing tyre, and it's things like that give you a slip angle that you can work with as a suspension and steering designer. Obviously, if you've got some sort of play in your steering system, then it becomes even harder to control that ultimate grip tyre. Whereas if you had quite the dull road tyre, which is probably more like the bottom dotted line, you can see that it doesn't matter what you do to the steering wheel, it's still got grip and it's still going to go around a corner. Again, so this is the plot. This is from physical testing. So here you can see the lateral force as a function of slip angle again, and each line indicates a different normal load. So as the load increases, the desired slip angle increases as well. So the steering process. So you're going on a flat road. Flat road's a pretty good approximation to make. So steering angle is induced by the driver. Driver turns the wheel turns, and the rubber turns. There's a delay in the actual rubber creating a slip angle from the real wheel rotating. This has got to do with the relaxation rate of the tyre. It can be approximated by approximately a third of the tyre's circumference. So the steering angle imposes a slip angle on the tyre, and then the slip angle then generates a lateral force. Now, another way to look at it is if you're going across a banked road, you've got a sliding lateral force trying to keep you up, creating a slip angle, and then you have to steer into it. So you can see that happening in both directions when you get that. So this unbalanced lateral force that happens when you create this front wheel slip angle creates a yaw about the centre of mass, and this yaw then generates a slip angle on the rear of the tyres. So this difference initially between the front and the rear is essentially your turn-in phase, and it can be quite drastic depending on your yaw inertia of the car, and essentially the delay or the response between the front acting and the rear reacting to it. So as the rear tyre then becomes to generate a lateral force to balance the yaw, this is when you get your sustained lateral force. And a good part of vehicle design is making that transition phase as small as possible such that the car's in the sustained lateral phase, and it's quite predictable and easy to model through that. So slip ratio. So similar to your slip ratio, your slip angle. Anytime you want to turn or generate lateral force, you need a slip angle. Anytime you want longitudinal force, you need a slip ratio. So in order to generate that, there is some form of slip in the longitudinal direction. So you can see the graph on the right at the top. You actually see peak grip is actually at 0.25 your slip ratio. So if you know anything about the Hoon law, you'll find that the Hoon law is fundamentally flawed, because if you've got any slip, any loss of traction between the driving wheels, you're breaking the law. You can't drive without getting rid of that slip. So fun fact for the day. So simple traction control systems take into account both your slip angle and your slip ratio of the tyre. It's pretty important to have a tyre model associated with that, otherwise lots of physical testing such that you can tune your system. Essentially, the traction control system that works controlling your slip ratio compares your driving wheels to the rolling wheels. So in a four-wheel drive, it becomes a little bit more difficult. You have to look at GPS and inertia of this car and things like that. But for simplicity's sake, we'll just look at two-wheel drive with the rear wheels driving. So if you've got your front wheels rolling, it tells you your actual vehicle speed. Then you can actually look at the slip ratio of the rear wheel and control that. Obviously, PID controller for that. You can cut fuel, ignition, and retard the spark just to reduce the power to the wheels and get back to your target slip. And slip can be negative, so when you're braking, it works in the opposite direction. So a lot of ABS systems will look at what wheel's locking up first, looking at your change in rotational wheel speeds, and actually pulse your brake pressure to get that target slip ratio back. So here we go. So this is some data from our race car. You can see that up top there you've got your ignition cut as a green trace and the fuel cut level. So the fuel cut is actually more intrusive when you've got your wheel slip increasing above the desired. So this might be a little bit confusing to look at if you're not used to seeing it anyway. But you can see the TC system actually cuts and imposes restrictions on the engine performance, and as a result your wheel speed actually decreases when you're decreasing the power. Anyway, so back to our steering now. So caster is one of our steering geometry factors. It provides a self-aligning effect from steering, so you might notice when you go around a roundabout, you let go of the wheel, tyre straightens up again. This is due to caster. It's essentially the forward inclination of the steering axis to the ground, and it introduces what we call mechanical trail. So mechanical trail is the difference between the vertical centre of the tyre and the intersection of the steering axis with the ground plane. And it's a combination of that with KPI that actually influences camber change when steering, and that opens up a whole new ball game of being able to tune how you steer the car and what's going on there. Caster also imposes caster jacking. As you turn the wheel, it actually tilts the wheel into the ground and pushes down harder. Through reactions in the chassis, which I might talk a bit more about on Wednesday at least, it actually pushes the opposite rear wheel down to the ground. So if you're turning inboard, you're turning right, for example, your front right wheel is being pushed harder into the ground, pushes your rear left harder into the ground, and can lift your inside rear. Go-karts are really good to see that. If you see someone racing a go-kart who knows what they're doing, turn the wheel, they lean out a bit, lifts that rear wheel off the ground, and because on a go-kart both wheels are connected by the solid axle, to eliminate the inside wheel slipping and slowing them down, lifts it up, problem goes away. So caster jacking is really important in car dynamics because it also has a pretty good influence on correcting oversteer. So when you're sliding out around a corner, the back end's going around, opening up the steering again changes that force balance and causes a rear axle to plant again so that you can drive out of a corner and not completely spin out. So before cornering actually occurs, caster jacking induces a yaw acceleration on the car due to imbalances in forces, and obviously it controls your jacking weight, so it affects your lateral load transfer. Again, go into that next lecture. Kingpin inclination, so if you're looking at the front of the car now, the kingpin inclination is the inclination of the steering axis in side view, and combined with caster, it actually affects the camber compensation and gain of the wheel. So as you turn the wheel, how much the wheel actually tilts into the ground. It's more generally a packaging constraint, and scrub radius is important. Scrub radius is the distance between the intersection of the ground and the centre of the wheel, or the centre of the contact patch, this point here. Scrub radius doesn't really add to anything other than self-aligning when you're under brakes. So if you notice, if you've got one wheel in a puddle, one wheel on dry bitumen and you brake, the scrub radius and the difference in longitudinal force will actually pull at different amounts. So an imbalance of forces creates a moment about the steering axis due to the scrub radius, turns the wheel and you can feel the wheel shaking or turning. It's generally, we try to eliminate a significant portion of that because it just adds load to the system and makes the steering system heavy. But it does give you a lot of room to put brakes and stuff inside the rim itself. So a lot of road cars have quite high scrub radius, and they run power steering to get her out of the negative side of things. And this here, it's probably worth having a look at later anyway, so you can actually take it all in. There's a 3D view explaining the combined forces and how they're reacted through caster angle and your KPI. And the next bit to consider is our tyre deformation again. So a big assumption is, that's always wrong, is assuming that your tyre is rigid. That's really not true. So Tyres have what we call pneumatic trail, and it's actually a stretching of the tyre contact patch based on the mechanical trail. So the movement between where it's at standard and then when it deforms, you've got a pneumatic trail, and that pneumatic trail is additional to your mechanical trail, and it's proportional to the load on the tyre. So when you're going around a corner, you might be at, say, 1G, you've got X amount of pneumatic trail, so you actually feel a moment through the steering system, which is a result of that force multiplied by your pneumatic plus your mechanical trail, and then your steering system ratios to feel that in the wheel. If you had, a mechanical trail an order of magnitude higher than your pneumatic trail, you would never feel that force being reacted through the tyre, and it's quite important for people driving race cars to get that feedback from the wheel, because it tells you how hard the tyre is working. And if you exceed that slip angle plot that we had up before, so if you go past the peak and the load actually drops off, you can actually feel that when your steering gets light, to open it up a little bit and get back into the appropriate range. So pneumatic trail is pretty important, and it's quite difficult to measure unless you've got a multi-million-dollar rig, but it's important to take that into account. KPI and scrub radius. So front-wheel drive cars often have negative scrub. Has anyone driven a front-wheel drive car? They put the foot down and noticed that the steering wheel turns to one side or something like that. This is a result of unbalanced wheel forces. When one wheel type turns to slip and it's not creating any force anymore, the other side's got a lot of grip, creates a moment about your scrub radius that actually turns the tyre itself. So you feel that pulling around, you know that one of your wheels is slipping a bit. And again, too large a scrub radius on front-wheel drive cars can lead to torque steer through that exact same mechanism. Simply going around a corner changes your load distribution on the tyres. If you've got the same driving force, it's going to change the longitudinal force of both of those wheels, and it steers the car. So that's why you generally don't see many high-performance front-wheel drive cars. So back onto the Ackerman concept now that we've got pneumatic trail, slip angles, slip ratios, things like that sorted out. As mentioned before, it was originally to avoid cutting ruts and gravel roads, and 100% Ackerman is essentially dynamic toe out, so it changes the inside wheel as the steering changes, so the two wheel angles change per the steering wheel angle. It's always a bit of a moot point when you're trying to discuss this with judges at Formula SA competitions, because everyone has a different definition of Ackerman. Generally, a plot of steering wheel angle versus wheel angle clears that up pretty quickly. So the Ackerman concept was invented in 1817 by a German dude, who I'm not going to try pronouncing his name, and then it was patented by Rudolf Ackerman for use on horse-drawn carriages in 1818. Now, it works really well theoretically for low-speed turns, because at low-speed turns you've got quite small slip angles, and at these low slip angles, obviously you're not getting a change from what's actually happening. Here we go here. So you can actually see now, if you introduce slip angles to the equation, the black line represents your no slip angle. The dotted line represents no slip angle, so your theoretical Ackerman. You introduce slip angles again, and the wheel's force direction is changing, and the black lines give you your true radius of curvature or center of rotation. So it's really important. This is the slip angle, probably only 5 degrees, but it has quite a significant change on the aspects of what's going on in the car. Here we go. So parallel steer is commonly what you see on older karts and whatnot, where both wheels turn at the same angle all the time. Obviously, you're going to have those wheels slipping to generate some sort of turning for the vehicle. Your Ackerman condition, so the inside wheel is actually changing relative to the outside wheel to maintain that point of intersection on the rear axle. And then you've got reverse Ackerman, which is it's different again. It's where the outside wheel is actually turning more than your inside wheel. You see this a lot in Formula 1 and other cars which have really high lateral load transfer. As you push down on the outside wheel, it gets heavier, and it also wants a high slip angle to generate the high force. As such, reverse Ackerman is used on those cars to maintain that situation and get the maximum grip out of both wheels. Positive Ackerman is the opposite, so that's when your inside wheel is actually steering more than the outside wheel. This is massively important Formula SAE. It's pretty well not known by a lot of teams, but you do a yaw vector analysis, so you look at the forces on each corner of the car. If you've got your inside front wheel at a large angle on turn-in, it creates quite a big drag effect and it pulls the car around that corner. So you can see that it's not always about making sure tyres aren't sliding, it's not always about having the most grip, it's about being smart with your yaw control, yaw generation. So as I said, Formula Y in Indy, they generally run anti-Ackerman, whereas for low-speed cornering, 100% Ackerman is desired. So all your road cars will have pretty close approximation to 100% Ackerman, as it reduces scrubbing the inside tyre, it doesn't overheat tyres, and things like that. So you can see Ackerman is a pretty good theoretical explanation of what's going on in your road car. You get into race cars and suddenly this thing gets blown out the water with way different concepts. Okay, so a few different steering systems. So rack and pinion, most commonly used. It's good at controlling forces and it's quite simple to manufacture. It's involved with a straight gear on the bottom and obviously normal gear on the top. You can see from your steering wheel input puts a rotation in and the output is a linear movement. So you can see the position of that from the box on the top there at least anyway, in a distance from the centre of the wheels actually changes your Ackerman ratio, and changing all the different system values. So your moment arm, your torque arm out on the upright of the wheel itself actually changes where you want to position that to achieve 100%. Then you can simply move that forward and back, maintaining the same geometry and get positive and negative Ackerman. Downside of that is you're quite limited in how much you can adjust that. Whereas if you have a bevel gearbox, a bell crank and a bevel gearbox, you get quite good packaging solutions, and by changing out the bell crank, which is essentially a triangular piece that it rocks about, you can change your Ackerman from anywhere. But I think I've managed to design something with 50% Ackerman through to 310% Ackerman. So there's a massive range, and by swapping out quite a simple part, you get massive adjustment scope. So this is our 2007 Motorsport car. Just in the bottom in the middle is a rack and pinion housing, which was custom made by, we got it designed here and sent out to a company in South Australia, actually manufacture. It's a pretty cool little piece of equipment, but you can see that the steering input from the steering wheel at the top goes through a uni joint, through a steering column, back into the rack and pinion. Then you've got your tyre rods, which are fed a linear displacement, and that rotates the tyres through the upright design, which you can't actually see too much in that picture. Next up is the 2009 design, I think this one is. So up the top you've got quite a compact bevel gearbox in there. It's quite neat because you don't have a steering column running all the way down to the car, and you can actually have, if the driver is sitting in front of the car, you can have the steering column go essentially right between his crotch. Whereas the other one you're looking at, it's going down towards your toes, so it takes up a long packaging room. And then at the bottom, you've got your bearing support and your bell crank, so you can already see that it's quite simple in supports. There's no uni joints to worry about compliance. And by swapping out that one bell crank, you can actually change so many of your system parameters. And then again, it's through your tyre rods, through to your wheels again. So that really wraps that one up. Next lecture on Wednesday is focusing on wishbone geometry, the 4-bar linkage of such systems, as well as 5-bar link systems and beam axles, things like that, and how they're different. We're talking about the importance of kinematics to control and performance. So bringing a bit across the slip angle stuff again, and your tyre loads. Why is that important? How does that get controlled? And again, tyres and springs and balancing the package, bringing it all together. So if you've got any questions, come down and have a chat to me quickly. Next lecture will be a little bit more full on, and we'll be going into a little bit more detail about 4-bar systems. Thanks for coming along, and I'll see you guys at, I think it's 1 p.m. Wednesday.